Welcome to the second and final video of section 3.1. I just found out from the YouTube gods that I can now upload videos longer than 15 minutes, so I will guarantee this will be the last one for at least this section. However, to save a little bit of sanity, I am going to limit it to about between 20 and 30 minutes in the future. So there still might be instances where I need to do 2 or 3 videos each section, but at least now it won't be every 10 minutes have to stop. So here we go. Number 5. Number 5, we are asked to actually graph the equation. We are asked to graph the tangent, and we're going to find specifically that tangent curve in this process. And so what we get is we need to find this our graph this y equals x squared plus 2x minus 8, realizing that there are several ways to do this. One of the easiest ways is to just start plugging in some values. But at a minimum, we do need to make sure that we include when the x-coordinate is 1, because specifically number 5 asks that. So I'm going to plug in 0. If I plug in 0 in for x, actually I'm going to plug in -2, -1, 0, 1, and 2. I need to see a problem, because that's what this is going to be. So if I plug in -2, this would be 4 minus 8. So that'd be -8. If I plug in -1, 1 minus 2 minus 8, that's -9. If I plug in 0, 0 plus 0 minus 8. 1 plus 2 minus 8. 4 plus 4 minus 8. Okay, so I've got some pretty good points here. And knowing that it is a parabola, I know it's going to reflect around the axis of symmetry. And to me that appears, okay, -2, 1, 2, 3, 4, 5, 6. -2, -8 goes there. -1, -9. 0, -8. 1, -5. So that would also be over here at -3. And 2, 0 would also be over here at -4, 0. And so we're going to get this nice parabola, at least as nice as I can draw on this computer. Something like that. Now here at x equals 1, we also want to find the tangent. Now we're going to find, there we drew the tangent, and technically we're done with this problem because we drew the parabola, we drew the tangent line. So we're probably okay, and in fact we won't go through the other business. But realize we could find the equation of this by doing what we just got done doing with problems 3 and 4. Okay, number 6, find the slope of the curve. Well, we know how to do that. Y equals x squared plus 9x, and this is at the point x equals -5. So the first thing we have to do in order to find the slope is we need to find the derivative. Y prime equals, okay, we're going to take this exponent, multiply by the coefficient that's in front. 2 times 1 is 2. Then this exponent is going to have 1 subtracted from it. 2 minus 1 is 1. The coefficient, or the exponent here, is 1. I'm going to take this 1 times this 9. 9 times 1 is 9. When I look at the exponent, it was a 1. When I subtract 1 from it, it's going to become a 0. X sub 0 is 1, so there's no more x's. So the derivative is 2x, and I'm not going to put a 1 there, 2x plus 9. So at x equals negative 5, just plugging in negative 5 into y prime, we get 2 times negative 5 plus 9, negative 10 plus 9, which equals negative 1. So the slope of this curve at x equals negative 5 is negative 1. That should not be a big surprise. Okay, example number 7. Example number 7 says find the equations of all tangents to this curve. F of x equals 1 over x. That has a slope of negative 1. So in other words, m equals negative 1, and we have to find all of them. Now, if we think about what 1 over x looks like, that's the reciprocal function. And so just very quickly, we're going to go like that and like that. That's more or less what the reciprocal function looks like. So where would they have a slope of negative 1? Well, about right there and there. So there appears to only be 2 places where that's going to occur. There's not a whole bunch, but we have to find both of them. Now the first thing we need to do, since this x is in the denominator, is to rewrite this in a user-friendly form. So 1 over x is x to the negative first power. This is algebra 2. Okay, so we've got x equals negative 1, and then now we're ready to find the derivative, because this is a much more user-friendly version. We're going to take this exponent, negative 1, multiplied by the coefficient that's here. Negative 1 times 1 is negative 1, and negative 1 x, we're going to take this exponent here and subtract 1 from it. Negative 1 minus 1 is negative 2. Now we need to rewrite it into its more common form, so that would be negative 1 over x squared. So the derivative of this is negative 1 x squared. Now we want to know, when does that equal negative 1? When does negative 1 over x squared equal negative 1? That's what we're asking. Negative 1 over x squared equals negative 1. Well, let's find out. Let's multiply both sides by x squared. So we get negative 1 equals negative x squared. Divide both sides by negative 1. X squared equals 1. And take the square root of both sides, so that x equals plus or minus the square root of 1, or plus or minus 1. So we know that the points are going to occur when x equals 1 and when x equals negative 1. Going back up here to our graph here. So we've need to find the points for each one of these. So when x equals positive 1, putting it back into the original equation, that'd be 1 over 1, or 1. When it's negative 1, once again, 1 over negative 1 is negative 1. So there are the 2 points that we're going to use. Each time we know the slope is negative 1, so now all we have to do is find the equation of both of them. And I was afraid I was going to lose all that work. If you have to, please rewind. So I've got y. Let's do the 1, 1 first. 1, 1 would be y minus 1 equals negative 1 times x minus 1. Y minus 1 equals negative x plus 1. Adding 1 to both sides, y equals negative x plus 2. Now if we choose the negative 1, we get y plus 1 equals negative 1 x plus 1. Y plus 1 equals negative x minus 1. And subtract 1 from both sides, y equals negative x minus 2. So here are the two equations that are tangent, are the tangents that have a slope of -1 on the original equation, which was 1 over x. Example number 8. Example number 8, we are looking at, if we look at the final question, it says find the instantaneous rate of change of distance with respect to the velocity. Now, this sort of leads to the second and third and fourth applications of derivatives once we get there. But for right now, we're just going to realize that if we're talking rate of change, then that means somehow we need to deal with derivatives. And so we know that the distance, according to the problem, is 0.05 v squared plus v. And since we need a rate of change, and it says rate of change of distance with respect to velocity. So in other words, we're asking what's dd, what's the rate of change, that's what these d's mean, of the distance with respect to the velocity. dd over dv means we're going to take the 2, multiply by the coefficient here. 0.05 times 2 is 0.1. And then we're going to subtract 1 from the exponent. Subtracting 1 from 2, we get 1. I'm not going to put a 1. Plus, okay, I have an exponent of 1. I multiply by the coefficient here, so that's 1. And then when I take the exponent of 1, subtract 1, I get v to the 0, which is 1. So dd over dv equals 0.1v plus 1. Now, specifically, this is the general rate of change, but notice what it's asking. We want to know what is the rate of change when the velocity is 47. So how we show that in this form is we say, okay, we want dd dv when the velocity is 47. Which is, that's why I put that down on the bottom when I had y prime. So now it's just a matter of 0.1 times 47 plus 1, which equals 4.7 plus 1, which equals 5.7. And this is 5.7 miles per hour. Now what this means is that's the instantaneous rate of change. I'm changing it 5.7 miles per hour. At this speed. And that's a little bit hard to grasp, and you don't really need to be able to decipher that yet. It will hopefully become a little bit more clear, quite a bit more clear a little bit later on. But for right now, just realize we need 5.7 miles per hour. Okay, number 9, we're going to have to do a little bit of thinking and thinking through on this particular problem. We have a rectangular steel plate expands as it is heated, and that is true of any materials. They'll either expand or contract. And we need to find the rate of change of area. Well, we know rectangular, the area is length times width. So that's the first thing we need to pull out from our bag of tricks in this particular problem. And we know that at the moment the width is 1.5 centimeters, the length is 2.4 centimeters, and we're given this information: dl dt equals 1.1 times 10 to the negative 5th, and dw dt equals 8.7 times 10 to the negative 6th. Now what this says is the rate of change of the length with respect to the temperature. That's all this means. So you do need to be able to decipher this. The rate of change of the length with respect to temperature is this. The rate of change of the width with respect to temperature is this. And look, and that's the way you want to look at these things throughout. Okay, now let's deal with the width first. Width is presently 1.5 centimeters. So how fast is it changing? Well, all we need to do is we need to take this 1.5 times the rate of change that's going on here, 8.7 times 10 to the negative 6th. And let's see. Sorry about that. I had to go get a calculator. Didn't have one handy. So, when we've got 1.5 times 8.7 times 10 to the negative 6th. Now I'm not going to spend time or try to spend time putting that into my calculator per se, but this is 13.05 times 10 to the negative 6th. Or in other words, putting this into true scientific notation, it's 1.305 times 10 to the negative 5th power. Likewise, when we look at the length, I know that's going to be 2.4 times 1.1 times 10 to the negative 5th. And so doing the multiplication there, 2.4 times 1.1 is 2.64 times 10 to the negative 5th power as well. And there's no adjustment required on this particular problem. But the thing is, have we determined how much the area is changing? Well, not quite yet, because we know the width is changing at 1.305 times 10 to the negative 5th. The length is changing at 2.64 times 10 to the negative 5th. And so the question becomes, how fast are they changing at the same time, or for the area? And so that would just be a matter of taking the change of length, 1.305 times 10 to the negative 5th, and multiplying that by the change in the width, 2.64 times 10 to the negative 5th, which equals, one final calculation, 1.305 times 2.64 equals 3.4452 times 10 to the negative 10th power. 3.4452 times 10 to the negative 10th power square centimeters. Square centimeters for every degrees Celsius. .4452 times 10 to the negative 10th, and that's square centimeters for every degrees Celsius that we go up. The 10th and final example for this section. Does the graph of that have a tangent at the origin, and give reasons for your answer? Well, the question becomes, does it have a tangent? Basically means, does it have a derivative? Now, in order for a graph or a function to have a derivative, two things need to happen. It needs to be continuous, first of all, And then it has to be what is called smooth. Now, what we look at when it talks about smooth, first of all, just some quick examples. This is not continuous, so it would not have a derivative at this point right here. So it's not continuous, but it is very smooth, nice and smooth all the way around. An example of not smooth would look something like this. Notice right at this point right here, it's not smooth, it's very pointed. So in order for a derivative or a function to have a derivative, not only does it need to be continuous, but it also needs to be smooth. So this is smooth, but not continuous. This one here is continuous, but not smooth. So with that in mind, we need to look at number 10 and see, is that smooth and continuous at the origin? And so what we're actually going to do here is we're going to bring up the calculator and graph this. Specifically, we're going to be paying attention to the origin, so we will want to change that or look at the window here right off the bat to see what does it do right at the origin. Now, so we go in here to the window. I'm going to do -2, 2, and 1, -2, 2, and 1, and I'm going to put y equals, clear out anything I had, and I want to do x cosine of 1 over x. Now that's going to give me everything except right at 0. Now notice that if we tried to plug in x equals 0 here, we would get an undefined function. So that's why they put the 0 equals x equals 0. Now as we graph this, look at what happens right at the, it goes up and then it comes down, then it goes up. You know, it's a little small sort of curve sort of thing going on right here. The question is it smooth right there? Yeah, it's smooth. It appears to be coming just along right through there and then stops about there. But it's not continuous. At least x cosine of 1 over x is not continuous. However, that applies for anywhere except where x equals 0. When x equals 0, we just fill in that point right there. Then all of a sudden it does become continuous. So with that in mind, it is both smooth and continuous. So the answer is yes. There is a tangent at that point.